So far, we've learned about representing integers in different number bases, specifically base 10, which is what we learned as kids, and bases 2, 8, and 16, which are commonly used in computer science. These different number bases are a lot like different units of measurement. Milliliters, gallons, and cups are all measures of volume, but each one is more useful in some contexts than in others, and we often have to convert from one measure of volume to another. Similarly, it's important to be able to convert between different number base representations. We've seen how to convert a representation from base 2, 8, or 16 to base 10, which is pretty simple, and from base 2 to either base 8 or 16, which is also pretty simple. Going from base 10 to any other base, on the other hand, isn't hard, but when we did it, it might have felt to you like guesswork. In this video, we're going to make the process of converting from decimal to other bases more foolproof through a simple and rigorous algorithm. First of all, an algorithm is a finite process or a set of rules that we or a computer will follow to make a computation or solve a problem. An algorithm, if correct, will have a definite start point and it will end after a finite number of steps with a correct result. For example, in school, we learned algorithms for multiplying two numbers together. In computer science, we have algorithms for all kinds of things, like sorting lists, finding the shortest path through a network, and more. Algorithms are at the core of computer science, and you will be visiting them regularly throughout this course and throughout your careers. We're going to describe an algorithm now that will convert a number from base 10 to base 2. And to set the stage, let's consider the following process that isn't really useful by itself, but it illustrates the main idea. So take the number 2,417 in base 10. Starting with this input, let's go through some steps. First, divide 2417 by 10 and record the quotient, how many times 10 goes into it, and the remainder, the amount left over. If you do the long division on this, which is another algorithm we learned in school, 10 goes into 2417 241 times with a remainder of 7. So the quotient is 241 and the remainder is 7. Note that the remainder must be less than 10 because we're dividing by 10. And if the remainder were 10 or greater, we could just divide again. Record both the quotient and the remainder. Now repeat this process, but use the quotient from the previous step, 241, as the new input. So divide 241 by 10. The quotient is 24 and the remainder is 1. Record both. Now repeat the process again by using the previous step's quotient as the new input. Divide 24 by 10 and you have a new quotient of 2 and a remainder of 4. Repeat again. Divide 2 by 10, and this yields a quotient of 0 and a remainder of 2. If we were to repeat this process more, we would be getting a quotient and a remainder of 0 every time. So once we get a quotient of 0, the algorithm terminates. Now, if you look at the list of remainders we kept, these are the base 10 digits of the original number, 2,417, in reverse order. Repeated division by 10, in other words, produces a list of the digits. So I want you to notice two things at this point. First, algorithms in computer science and in real life often work by repetition. You have just a few lines or even one line of code that performs a simple operation, and the algorithm simply repeats or iterates over these instructions until some kind of condition is met, and then it stops. Remember that concept as we explore algorithms in the future. Second, let's be honest, this algorithm on its own is pretty much useless because we don't need to go through all these steps to see the digits of a decimal number. We just look at it. The power of the algorithm really comes from the fact that we can modify it to do other things. In fact, this very algorithm can be modified just slightly to give us the binary digits of the same number. All we have to do is change the instruction of dividing by 10 to dividing by 2. When we divide an integer by 2, we always get a remainder of either 0, if the number is even, or 1, if it's odd, and never anything else. So those remainders are going to be bits, and those bits are the digits of the binary form of the integer we start with. Let's see how this works with a simple 2-digit decimal integer, 37. Again, the way the conversion algorithm works is that we will repeatedly divide the input, this time by 2, record the quotient and the remainder, and then repeat this process using the previous step's quotient as the new input, and then stop when that quotient is 0. So first, 37 divided by 2 is 18 with a remainder of 1. Record both 18 and 1 in memory. Next, 18 divided by 2 is 9 with a remainder of 0. Record those two in memory. Next, 9 divided by 2 is 4 with remainder 1. Then 4 divided by 2 is 2 with remainder 0. Next, 2 divided by 2 is 1 with remainder 0. Next, 1 divided by 2 gives a quotient of 0 with a remainder of 1. So record those in memory, but then stop since the quotient has reached 0. To end the algorithm and to get the binary representation, construct a string from the remainders in the reverse order in which they appeared: 1, 0, 0, 1, 0, 1. Let's check to make sure this is right. In binary, 1, 0, 0, 1, 0, 1 is 1 times 2 to the 5th plus 1 times 2 to the 2nd plus 1 times 2 to the 0, which is 32 plus 4 plus 1, and that is indeed 37 in base 10. Now you try it. In the very first video, we converted the base 10 integer 275 to binary without this algorithm, and the answer was 1000 10011. Pause the video and take a few minutes to work through the algorithm to convert 275 in base 10 to this number in binary. Here's the work for this process, and as you can see, it does indeed produce the right binary representation. And that's an algorithm for converting a number from decimal to binary. But you wouldn't be wrong to have a lot of questions about this algorithm. For example, why does this algorithm produce the correct binary form of the integer? Are we sure that it always does produce the correct binary, or did we just get lucky with these examples? Are we sure that the algorithm always terminates, or is it possible that we could start with an integer that throws the algorithm into an infinite loop? These are questions that, as computer scientists, we have to ask and answer about every algorithm we meet. It's not enough just to be able to write code and compute answers. Kids or even AIs can do that. What we have to be able to do is reason about algorithms like this and explain why they work in all cases, not just the ones we choose or observe. A million examples will not do this for us. We need to use mathematics and mathematical reasoning to get into the deep machinery of computing processes to help us understand things that simply writing code cannot explain. Being able to use mathematics to go beyond code and reason about computational processes is a major learning goal for this course, and we will be revisiting it repeatedly throughout everything we do. For now, we are going to take it on faith that this base conversion algorithm really works, but we will need to come back to this algorithm later once we have more tools for thinking about algorithms and think about why it works. Notice that this algorithm, while a little tedious to do by hand, is quite fast because every iteration of the loop where we divide and record the quotient and remainder literally cuts the new input size in half. That means that it will scale up well. While it obviously takes more steps to convert a large integer than it does a small one, a number with twice as many decimal digits does not necessarily take twice as many steps. Another important concept we'll be thinking about in this course is just exactly how algorithms scale up when the input size increases, and how that scaling up might be modeled with mathematical functions. Another great thing about this algorithm is that it can be modified to convert a decimal integer into any base, not just binary, simply by changing the number we divide by. For example, if we wanted to convert the number 1982 from decimal to octal, just run the same process but divide by 8. In this case, 1982 divided by 8 is 247 with remainder 6. 247 divided by 8 is 30 with remainder 7. 30 divided by 8 is 3 with remainder 6, And then 3 divided by 8 is 0 with remainder 3. We stop here because the quotient is 0 and list back the remainders in reverse order to get 3676, which you can check is actually 1982 in octal. And here's an example in hexadecimal that shows how fast this can be. Look at 161,067 in base 10. That number divided by 16 is 10,066 with remainder 11. 10,066 divided by 16 is 629 with remainder 2. 629 divided by 16 is 39 with remainder 5. 39 divided by 16 is 2 with remainder 7. And then 2 divided by 16 is 0 with remainder 2. So the base 16 representation of 161,067 is 2752B. Remember, B is the hexadecimal for the number 11. Again, we have not attempted to explain why this works other than by analogy when we divide by 10. To prove the algorithm works for any base will require some mathematical tools we'll be encountering in later videos. So in this video, you learn an algorithm for converting from base 10 to any other base you want. And we've introduced some important concepts about algorithms, what they are, the importance of reasoning through them, and the concept of understanding mathematically how they scale up. In the next few videos, we're going to focus on binary representation specifically and think about how computers do basic arithmetic in base 2.